Hi, I'm Cheryl Leach. In this exercise, we're going to sketch the graph of an equation. We're going to be looking at y equals 3x to the fourth plus 4x cubed. We're going to use some algebra techniques as well as all of the calculus techniques that we've been studying in this chapter. So let's begin with a little algebra. To begin with, a nice feature to find on any function is the x-intercept and the y-intercept. So we'll begin with the x-intercepts. Where do x-intercepts occur? They happen when the y-coordinate is equal to 0. So let's set y equal to 0 and solve for x. Luckily, I can factor an x cubed out of my expression. So I've got x cubed times the quantity, 3x plus 4. I have two things multiplied together that equal 0, so one of them must be 0. So either x cubed is 0 or 3x plus 4 equals 0. Solving each of these for x, I noticed that in the first case, x will be equal to 0. And in the second case, I need to subtract 4 from both sides and divide by 3. That will give me x equals negative 4/3. Let's go ahead and plot those on my graph. So I know that I'm going to have x-intercepts at 0, which is right here, and negative 4/3, which is going to be right about here. Okay, now let's talk a little bit about y-intercepts. Y-intercepts occur when the x-coordinate is 0. So if I plug x equals 0 into my equation, I end up with y equals 0. Notice I already have that point on my curve. The origin is both the x-intercept and a y-intercept. All right? So now that we've done a little bit of algebra, let's move on to calculus. But let's wait one more minute. I forgot about one important thing about algebra. Let's think domain. Are there any values of x that you're not allowed to plug into this? No, you can plug anything you want. So the domain will be from negative infinity to positive infinity. Now that we've taken care of that detail, we are ready for the calculus. So the first thing we're going to look at is when is the graph increasing and when is it decreasing? In order to determine this, we need to look at the first derivative. So let's find dy dx. The derivative is going to be 12x cubed plus 12x squared. I want to know when this derivative is 0 and when it's undefined, to find the critical numbers. Well, it's a polynomial, so it'll never be undefined, so I can concentrate on when does it equal 0. So 0 equals 12x cubed plus 12x squared. In this case, I can factor out a 12x squared. And when I do that, I'm left with an x plus 1. Either 12x squared equals 0 or x plus 1 equals 0. In the first case, x is going to equal 0. And in the second case, x is going to be equal to negative 1. So those are my two critical numbers. I'm going to hold on to that for just a minute and talk about concavity. Well, we know that a graph we can determine whether a graph is concave up or concave down by looking at its second derivative. So let's go ahead and look at the second derivative. The second derivative will be 36x squared plus 24x. Again, I'd like to know when this is 0 and when it's undefined. So it's never undefined, but it could equal 0. And we can factor out a 12x, and we're left with 3x plus 2. Two things multiplied together that equals 0. Either the 12x is 0 or the 3x plus 2 is equal to 0. Well, when do these things happen? Well, this happens when x is 0. And here I'm going to subtract 2 and divide by 3. So that's going to happen at negative 2/3. All right, so I have all of my key points here. So I want to be able to take a look at my graph and say, when is it changing? Well, I know that this thing is defined for all real numbers. So I'm going to start with negative infinity. And I'm going to move to my first key point. Well, if you look at this, I've got critical numbers at 0, -1, 0, and -2/3. Those are going to be all the important spots. So the first of those, or the smallest one, would be -1. So I'm going to look at the interval from negative infinity to -1. Then I want to see what happens at -1. Next key point is going to happen at -2/3. So we're going to look at the interval from -1 to -2/3. And then see what happens at -2/3. The next of my critical numbers is 0. So I'm interested in what happens from -2/3 to 0. And then what happens exactly at 0? I've used all of my critical numbers, so the only thing left to do is to see what happens from 0 to infinity. All right, let's look at some features. The second column, I want to evaluate my function. Well, it doesn't make any sense to evaluate a function on an interval, so I'm only going to be filling in the squares that correspond to given points. So I want to know what is the function value when my input is -1. So I'm going to plug that in to the original equation. And if I do that, I'll have 3 minus 4, which gives me a -1. Next, I'll plug in -2/3. This one's a little more complicated. When you plug -2/3 into the original equation, you get -48/81. That's about -0.6, so I'm going to approximate that. Then we have to evaluate the function when x is 0. That one's much easier. When x is 0, y is 0. Now I want to fill in my derivative column. Well, in this case, I do want to find out what's happening on intervals. So this time I'll be filling in all the squares that correspond to the intervals. All right, so let's take a look at the first derivative. I want to take a test point on the interval from negative infinity to -1. So try any number on that interval. Let's say -2. Right? This is a convenient spot to plug in your test point. Notice that it's still the derivative, but it's the most factored form of it. So when I plug -1 in at that location, I'm going to get, or excuse me, -2 at that location, I'm going to get a positive times a negative, which is a negative. Let's do the same thing on the interval from -1 to -2/3. Right? I need to pick a point on that interval. Let's try -3/4. I'm going to take 12 times -3/4 squared, that's a positive number, and then -3/4 plus 1, that's a positive. I've got a positive times a positive, that's a positive. Continuing on, I need to look at the interval from -2/3 to 0. Take a test point. How about -1/2? 12 times -1/2 squared, that's positive, and -1/2 plus 1, that's positive. So a positive times a positive is positive. And then finally, the interval from 0 to infinity. Pick any point on that interval. Let's say a 1. 12 times 1 squared, that's positive, and 1 plus 1 is positive. Again, a positive times a positive is positive. Let's do the same thing now for my second derivative. Right? This time, I'm going to plug it into my test points into that form of the second derivative. Again, it's the most factored form. That's the easiest way to figure it out. So a test point, anything between negative infinity and -1. Let's try -2. 12 times -2, that's negative. And if I plug a -2 in here, I'm going to have a -6 plus 2. That's also a negative number. A negative times a negative is a positive. Now let's try the interval from -1 to -2/3. Let's try -3/4. So 12 times -3/4, that's a negative number. And -3/4 times 3, well, that's -9/4. And when we add 2 is 8/4. So that's going to end up being a negative number as well. And a negative times a negative is a positive. Take a test point between -2/3 and 0. Again, let's try -1/2. 12 times -1/2, that's negative. And -3/2 plus 2, that's positive. A negative times a positive is a negative. And then finally from 0 to infinity. Let's just try 2. 12 times 2, that's positive. And when I plug a 2 in here, I'll have a 6 plus 2, that's positive. A positive times a positive is positive. Now we're going to put all of this information together. Let's see what's happening. On the interval from -infinity to -1, my graph is decreasing, but it's concave up. So decreasing, concave up. On the interval from -1 to -2/3, it's increasing and concave up. On the interval from -2/3 to 0, it's increasing, but I'm changing to concave down. Increasing, concave down. And then finally, on the interval from 0 to infinity, I'm increasing and concave up again. Well, notice that I've skipped those points. Let's fill in the information, see what's happening at those locations. So at -1, -1, notice there's no change in concavity, but there is a change from decreasing, so the graph is falling, and then it increases. That's giving me a relative minimum. At the point -2/3 and -0.6, notice no change in the increasing-decreasing nature, but there is a change in concavity. That makes it an inflection point. And then finally, at the point 0, 0, again, it's strictly increasing here, so there's no change, but there is a change in concavity, which makes it another inflection point. I have a lot of information here, but there's one more piece of information that I have not yet discussed, and that is the existence of asymptotes. If I look at the original problem, though, I notice that I have a polynomial. Polynomials do not have asymptotes, so I don't have to worry about that aspect of the problem. Okay, we're ready to put it all together. From our chart, we're going to take all of our key points and put them on our graph. So I know that -1, -1 is an important piece of this puzzle. So -1, -1 is right here. Okay? -2/3, -0.6 is also important. So -2/3 and -0.6 is going to be right about here. 0, 0, I already have on my graph. It was one of my x-intercepts. And don't forget, I already have my x-intercept from earlier. These are the key points on my graph. Now I have to fill in the details. So I know that from -infinity to -1, that means until I hit this point right here, my graph will be decreasing and concave up. So it's decreasing and concave up. I also know that at -1, -1, I have a relative minimum, so that there's a nice turn in my graph at this point. Once I hit that relative minimum, I begin to increase, but I'm still concave up until I hit the point -2/3, -0.6. That's an inflection point. Once I hit the inflection point, I'm going to continue increasing, but it's going to be concave down. So I'm going to continue to increase, but the concavity changes. Then when I hit the point 0, 0, again, I'm continuing to increase, but I switch concavity again so that it's concave up. And that's how the graph will continue. I hope this helped. Thanks.